So in this video, we're going to talk about Le Chatelier's principle. And so Le Chatelier's principle basically states, when a stress is applied to a system at equilibrium, the equilibrium shifts to relieve the stress. So now when we use the term stress, it just simply means anything that disturbs the original equilibrium, okay? Now, what can disturb an equilibrium? Well, several things could disturb the equilibrium. So what are those things that could disturb the equilibrium? Well, by changing the concentrations of, actually, let me write like this. By changing the concentrations of the reactants or products. So if you were to add or take away reactants or add or take away products, that's disrupting or disturbing the equilibrium, okay? And so then the reaction is going to shift to relieve that stress or to reestablish an equilibrium, okay? If you were to change the temperature of the system, all right, by increasing or decreasing, depending what you do and depends on the reaction, you are disturbing the equilibrium, all right? And so the reaction is going to shift in such a direction to try to reestablish the equilibrium. Or by changing the pressure that's being exerted to the system, all right? And so by doing that, you will also you are disturbing the equilibrium, and so the reaction is going to move in such a way or shift in such a way to try to reestablish an equilibrium. All right. Now, one thing I want to know are catalysts. Catalysts does not change the equilibrium. The only thing a catalyst would do is it will make the reaction get to equilibrium faster, okay? But it's not going to shift the equation in any direction, all right? And so what do I mean by shifting it? All right, so if you consider a chemical reaction like, and this here's just a general one. Okay, by doing any of these changes, you're going to, actually, let me erase this. And I'm just going to draw like this, same size. All right, by changing any of these three, what you're going to do, you're basically disrupting this equilibrium to where that maybe certain changes where it's going to, the forward reaction is going to move faster than the reverse reaction. When this happens, all right, when the forward reaction, or let me say the rate of the forward reaction is faster than the rate of the reverse reaction, we say that this reaction has been shifted to the right. Okay, that's what that means. When something's shifting to the right, the forward reaction is faster than the reverse reaction. Okay, and this will continue to take place up until equilibrium could be reestablished. So then what happens is, over time, the forward reaction will slow down, the reverse reaction will speed up, and then when the rates of the reaction are exactly the same, then we're back at equilibrium. Equilibrium has been reestablished. Okay. Now, it doesn't mean that it goes back to the original concentration. All right, depending on what you did to it, it may not go back to the original concentration, but the rate of the reactions, in which the rate that you make products versus the rates you make wow, the word messed up, but the rate that you make reactants, the rate that you make products and the rate that you make reactants, once they become the same again, then equilibrium has been reestablished. All right, may not be, as I said earlier, the original concentrations, but the rates are the same. All right, now let's say that the rate of the forward reaction, so you applied a stress, and the rate of the forward reaction is slower than the rate of the reverse reaction. So this means, right? So if you were to erase this here, so this means that that the rate that the reaction is going this way is much faster than the rate that's going this way. Then we said that the reaction has shifted to the left. Okay. All right, so that means you're making a lot more reactants than your products, but over a period of time, the rate of the reverse reaction will slow down. The rate of the forward reaction will speed up until equilibrium has been reached again or has been reestablished. All right, and so that's essentially what that means. All right, as for things are being shifted to the left and to the right. Now let's talk about each of these. So here, let's talk about each of these changes that we can do as for changing the concentrations or changing the temperature and change the pressure. How does that affect the equations themselves? All right, so let's look at effects of concentration, okay? Now, if I were to increase a concentration of a reactant, all right, so we're increasing concentration of reactant. All right, so what's going to happen if you increase the concentration of the reactant, all right, then what's going to happen is that the chemical reaction, it's going to shift to the right. So the forward reaction will increase, and thus the equilibrium is pushed to the right, or the reaction will be shift to the right. All right, so like for example, let's kind of see what I mean by this. All right, so here's a chemical reaction where carbon monoxide plus water forms methane. All right, methane gas. If this thing was already at equilibrium, so it was at equilibrium one point, okay, and then if I add carbon monoxide, what's going to happen is that the reaction will actually do the opposite, okay? Because I added carbon monoxide, the reaction is going to then try to take away carbon monoxide from the overall system. And by doing that, what's going to happen, for it to get rid of the carbon monoxide, all right, it's going to push the reaction forward. The forward reaction is going to move faster. The reverse reaction is going to move slower. All right, so what does that mean? If I add more carbon, so if I add carbon monoxide, then what's going to happen, you're going to have the reaction is going to take the hydrogen, all right, collided with the carbon monoxide. Then what you're going to see here, then you're going to see a decrease of the amount of hydrogen is there. And then what's going to happen, because you see a decrease of the hydrogen in there, then you're going to also see an increase of methanol because you're driving the reaction to the right. So if you add more reactants, or either the reactants, whatever the case is, if you add a reactant, then you're going to drive the reaction to the right, okay? Because the reaction typically, and this is always the case with all the concentration ones I want to talk about, is that anytime that you do any type of stress to the chemical reactions, in terms of concentration, the chemical reaction is going to do the opposite to relieve the stress. All right, so in this case, if I'm adding CO, then it's going to try to get rid of the CO I've added. By getting rid of the CO, in a way, it's going to get rid of the carbon monoxide. It's going to cause the carbon monoxide to react more with the hydrogen, and then you will see that there's a push to make more methanol. Okay, CH3OH. Now, what if I increase the concentration of the product? All right, so here's methanol. All right, so what if I add methanol? Okay, if I add methanol, then what we're going to see here is that there's going to be a shift towards the toward the reverse side, and the to the forward side, the forward reaction is going to be much smaller. The reverse reaction is going to be much larger. All right, because if I add product, then the reaction is going to try to take away what I just added. In order to take away what I just added, the reaction has to move the other direction. All right, and so in this case, this reaction is going to move towards the left. All right, more towards the left, faster than it's moving towards the right. And then what's going to happen is that then I'm going to increase the amount of each of my reactants I make, or I have. So I'm going to increase the amount of carbon monoxide I'll have, and I'm going to increase the amount of hydrogen gas that I have, because I increased the concentration of the product. I physically increased it. And so it's going to move the reaction in this direction. So the next example I want to show is, what if your system was just equilibrium and you decide to take away or decrease the concentration of a reactant. All right. So for example, let's just say that with this reaction, I managed to find a way to decrease the amount of carbon monoxide. All right. So I take away, all right, carbon monoxide. If I take this away, what's going to happen? Well, as I said before, the reaction is going to do the exact opposite of what you did to the reaction. So because I took carbon monoxide away from the reaction or from the system, then the reaction is going to try to replenish the carbon monoxide. And so in this case, then, if it's going to try to make this, then that means this reaction is going to move primarily in the reverse direction and just a little bit on the forward side. All right. And then eventually the reaction is going to reach equilibrium again. All right. As the reverse reaction rate slows down and the forward reaction rate increases until they're both equal. But you're going to take away, if you take away CO, all right, the reaction is going to try to create the CO, all right, or try to replenish it. And so this simply means what's going to happen is that you're going to increase the amount of H2 you have because it's moving towards the left side, and then you're going to decrease the amount of methanol that you have. Okay, and so this is how it works when you're decreasing the concentration of a reactant. Now, if you are decreasing the concentration of a product, all right, and so like for example here, if we take this and we're decreasing this product here, all right, the reaction is going to do the exact opposite. If I decrease the product, the reaction is going to try to replenish what I just decreased. And so in this case, what we'll find is that the forward reaction is going to be much higher. The rate of the forward reaction is going to be higher than the rate of the reverse reaction. All right. And so then what's going to happen that over the period of time, the amount of carbon monoxide you have will decrease, and the amount of H2 or hydrogen that you have will decrease, so because you're moving towards the right, all right, faster than you're moving towards the left. And eventually over a period of time, the rates will kind of settle themselves out, and then equilibrium will be established again. All right, so that's the thing about concentration. So it really just kind of depends if it's a reactant or product, and also depends if you're either adding or taking those substances away. All right, so now we're going to look at how temperature affects the equilibrium. Now, temperature, usually it's shown by, when we're talking about temperature, it's either shown that if the process is endothermic or exothermic, right? And so, like, for example here, if you put heat here, all right, for a equilibrium, this tells us that this process was endothermic. All right, it needed heat in order for the reaction to take place. Or you could also find that heat's placed on the product side, All right, that means heat has been the heat has, it's a product, so this reaction has released energy, and so thus this is an exothermic process. Now, when it comes to energy or temperature, and to seeing how you change the temperature, how it's going to affect the equilibrium. All right, wherever you see the heat, you will treat heat as that substance. All right, so like in concentration, when we talked about concentration, we talked about what it means to change the reactants. All right, if you increase the reactants, this is going to the reaction is going to shift to the right. If you decrease the reactants, the reaction is going to shift to the left. If you increase the products, the reaction is going to shift to the left. If you decrease the products, the reaction is going to shift to the right. Okay, this is the same thing that's going to happen with the energy, right? And so all depends on where heat is and if you increase the temperature or not. Okay, and so for example, let's look at this example particularly. You notice heat is a product, so I'm going to treat it like a product. Okay, so like for example, if I was to increase the heat, all right, of the system, if I increase the heat of the system, what's going to happen? Well, if you're increasing a product, all right, the reaction is going to do everything it can do to decrease that. So that means my reaction is going to move to the left. All right, and so let me go ahead and erase this. And so what's going to happen, the reactions most likely is going to move towards the left. All right, and so you will make more carbon monoxides and hydrogen, and then you will have less methanol. So that's if heat was a product side and you're increasing the heat. If you increase the heat, then you have to decrease, the reaction is going to try to decrease the heat. Okay, and so that's basically the way that you want to kind of look at it in terms of temperature. So if heat's on the product side, treat it like a product. If heat is in the reactant side, treat it like a reactant in terms of how it affects the chemical equation and the chemical equilibrium. Now let's look at how pressure affects a chemical equilibrium, right? Now pressure is also one of those things that you have to look at each equation because each equation is different, and the pressure is going to affect the equation in different ways. All right, but the concept is it's pretty much the same throughout. All right, so if you were to increase pressure of the system, basically what's going to happen is that the reaction is going to favor the side with fewer moles of gas. All right, and it has to be of gas specifically. Okay, if you were to decrease the pressure, it's going to favor the side with more moles of gas. Okay, so let's look at this example that we have in front of us. All right, so with the carbon monoxide plus hydrogen gas yields methanol gas. All right, so if I was to increase the pressure, so I'm increasing the pressure here. Okay, which direction is this thing going to shift? Well, we're going to look at the one that has if you notice, we're going to look at the one that favors the side increasing pressure. We're going to look at the side with fewer number of moles of gas. How do we figure that out? Look at our coefficients. Okay, so the reactant side has 3 moles of gas, 1 for carbon monoxide and 2 for hydrogen gas. And then on the right side, you only have 1 mole of methanol. So it's because increasing the pressure will favor the side with less moles of gas, then we could see that in this reaction specifically, the forward reaction is going to be much greater than the reverse reaction. All right, so you're going to you're going to produce more of the methanol if you were to increase the pressure. But what if you decrease the pressure of the overall system? All right, so we're going to decrease the pressure of the overall system. What takes place? Well, if we decrease the pressure, it's going to favor the side with more moles of gas. All right, so when we're looking at this, all right, here's the mole of carbon monoxide. Oh, this is supposed to say 2 moles of hydrogen, right? And then over here, we only have 1 mole of methanol. So since the reactants have more moles of gas, all right, the reverse reaction is going to be true, is going to be larger than the forward reaction in this case. All right, and so then we could say that the reaction is going to shift towards the left because there are more moles of gas in this case when you decrease the pressure of the system. Okay, so this is how so these are all the different aspects of Le Chatelier's principle.